And this is the libhal meeting. All right, we have a lot of items to go over. The TLDR is we're going to be cleaning up. I'll be cleaning up the organization repo. We're going to be removing some fields from the HAL serial API. There's going to be a new interface called HAL socket. We're going to go over that. We're getting rid of libxbitset, that confusingly named library, which is the HAL bit library. I'll go over that as well. libesp8266, the device library for the ESP8266. But embedded into that is also a demonstration of how to make multi-target applications, as well as also some HTTP utilities. We're also going to go over worker objects, a new design paradigm within libhal, as well as also byte stream pipelines. And then we're going over how to parse serial data, discontinuous serial data, using these two new things. So first off, clean up the organization. The following repos are basically being moved. They're being moved out of libhal to my user. Why? They were pretty much my projects originally, and they don't make sense inside libhal. So I'm just kind of bringing them back to mine because I don't think they represent the quality we want to have on this organization. So libhal telemetry. I pretty much archived it, and it's still in the libhal repo, but it's not going to be used. We'll be using web serial for everything else. This is an older version of the web serial project. libcore was back in the day when I was working on SJCDev 2 v3, and it's not really necessary anymore, so I kind of brought that back in. I brought this back in as well. It's basically SJCDev 2 to be more modular with its own build system and crap like that. Not a very good, it wasn't a very good design. It eventually turned into libhal. Also, the SAMI app, which was supposed to help out with SJCDev 2 v3, that's also moved over to me. Not really going to do anything with it. Might just archive it because I don't really care to work with it at all ever again. GCC, ARM, NUN, EABI, Pico libc. This is a variant of the ARM, NUN, EABI compiler, but with the Pico libc C library. Has a lot of benefits to it, but it's not like we're really using it anywhere, and we're not going to super advertise it. And if people want to do it themselves, they can do it themselves, but it's not really libhal related. Next up is the starter project for v3. CVP build, which was my little dummy project for seeing what it would be like to build projects using C++ directly. I still like the idea a lot. I kind of favor it quite a bit, but totally understand that, it's not really probably going to go anywhere, and we shouldn't focus our energy on that. And SJCDev 2 in the future will be moved back to my repo. Libhal should be libhal and just libhal stuff. SJCDev 2, I don't think really fits being in libhal, and it will be moved once the last set of users are moved away from it. Not just the robotics team, but possibly any other clubs, any other classes at SJSU that may be still using it. So I'm going to wait a while before I move away from this. But I think at this point, given after COVID and a lot of the teachers moving away from using hardware for their classes, there shouldn't really be any users of it. So yeah, that's pretty much that little spot there. Any questions or comments in this for this? Cool. Next up, libhal serial API is getting a slight change, a little bit of a haircut on one of the structures, the return types. Now, normally in the future, when we fully release, removing items from return types, or really from any of the APIs, is going to be a pretty big API break. And it's something that we will not take lightly. So we have to be very careful to make sure we don't put things in that we don't plan to ever remove. I still kind of look at this return type and I'm not fully sure. But one of the items that I was certain need to be removed was the remaining field. Basically, when you pass some data into the serial read function, you basically pass in a buffer that you want to have filled. What it will return is the actual data that was filled up. So the span will be the start of that particular pointer and the length, as well as also the available amount of data left, as well as the capacity. Now, the problem is that the remaining just told you what was left afterwards, which is really easy to calculate, but it felt weird that the driver had to do this calculation for the caller. The caller, if it wanted that information, calculate it themselves. So it felt like an extraneous bit of work that the driver had to do that it didn't need to do. So it's a slight optimization, and we removed it from the read return type for the read function for serial. Yeah, that's pretty much that. Any questions on that? All right. HAL socket interface. So this will allow us to basically talk to socket-capable devices. The API follows the Berkeley sockets, but only really includes the write/send function as the read function. The other APIs like socket, connect, and close are handled through RAII. Now I'm going to explain the Berkeley sockets real quick before I go into the actual interface. So if you've done any networking before, you may have seen stuff like this. So if you want to create a very basic web server and handle the TCP communication yourself, you can use this. So here's the TCP socket flow diagram. If you're a server, you have the step of creating the socket. So the first function you call is socket. That just pretty much gives you back a socket ID and allocates the memory for it. Then you have bind. Bind allows you to bind the socket to a particular port and I believe also potentially a local address. Listen basically allows your device to start listening in for any incoming data. Accept means that you've gotten some sort of, means that you're allowing yourself to accept incoming connections. Then some connection comes in. The lower level hardware handles the handshake stuff. And from this point, you can then ask to receive information. It's a blocking operation. If the other client side has sent some data, you will receive it. And then from there, you can either send some data, you can go back to receiving, waiting for some new data to come in. You can keep cycling through this over and over again. It's a server. So you receive stuff, and then you serve something back. And that's just your flow. And if there's ever some sort of end message, you can either receive that end message and close your socket, or simply just close that particular connection that you have. On the client side, it's a lot simpler. You basically create your socket. You connect to some server with an IP address port number, or some other combination of stuff. Then you send some data. You then receive back a response back from your server. And if that's all you need to do after that point, you can either keep doing this over and over again while keeping the connection alive, or you can just close your connection. Those are Berkeley sockets. Now, the thing about Berkeley sockets that don't really, the Berkeley sockets were built back in the day when C was king. So you needed a function for every single step of the way here. Although, to be honest, I feel like that there could have just been a server socket that did all 4 of these all at once. I don't understand why there needed to be a separation between each one of these. Like why you need to allocate and then separately bind, listen, and then start accepting information. Maybe there's some stronger rationale out there. If someone here knows or knows someone they could talk to who could explain this in deeper detail, that'd be great. But otherwise, otherwise, the idea that I have is that all this should be handled with RAII. RAII standing for, again, resource allocation is initialization, meaning that once you created the object that is your socket, it should have pretty much done all the work you need in order to get everything set up. Once you have acquired your resources, it should have also initialized the device or initialized the thing. Specifically, we're just looking at client-side sockets. It only really has a send and receive function. The socket and connect functions are basically encapsulated in creating the object itself. And you may be wondering, well, how do you close the socket? Well, that's when the socket goes out of scope, when it basically is no longer valid and deletes itself. So going back here, look at the actual interface. We can see here, I actually explained that section here. We have the types of sockets, which are TCP, UDP, and SSL. We can also expand that to a larger set as we find them. We have our write return value. We have our read return value. Write just returns back how much data you actually successfully sent. Read returns back how much the buffer that's been filled up. And it's real simple. You just have a write function that returns back a result or write. And then you also have a read function that returns a result or an error result or a read type. And then a virtual socket destructor. And that's about it. It honestly looks very similar to like a serial port, just without the configuration. And that's pretty much the socket API. This is going to be, I go over this now because this is going to be useful for discussing the other things like libesp8266 and its socket drivers. But yeah, any questions about socket, the socket API? Cool. All right. Now to move on. So that's the socket API. We'll go back into that in a little bit once we get to the next slide on libesp8666. But before we get to that, I want to talk about libxbitset and why we're replacing it. Basically, I want to remove coupling to standard bitset. Standard bitset can be quite annoying to work with just on its own. The code was looking pretty kind of ugly, not going to lie. I'm trying to work with it very closely. And the API itself isn't very ergonomic. And because of all these things, I wanted to have a cleaner, simpler API that may also be easier for the compiler to compile down and come up with very efficient source code for. And I'm still not sure if it should be its own library or not. I think that there will be at some point where all the different libraries, like the thing we're going over called like workers and streams, all get put into their own dependencies or into their own libraries to be used on their own outside of libhal. And libhal can be simply just a set of interfaces, and that's about it, and maybe a couple of utilities here and there. The cool thing about that is that we don't have to worry about API breaks if that happens. The cool thing about that is that you can add dependencies to libhal that are parts of itself and not break any of the users downstream, because they don't have to add any more. They don't have to add any additional utilities. Whatever the dependencies of libhal are the dependencies of anything one that uses libhal. So splitting them up into their own separate parts should be perfectly fine and easy to do without breaking one. To give an idea of how this new library looks, I'll just show you what it looks like directly. So the systick library for libarm cortex has been updated to use it now. I'm still working on getting liblpc40xx working with this as well, but I'm also making a lot of changes here. Note that some of this code's actually, some of these parts are kind of broken. So we have this hal bit modify object. You pass it in some sort of volatile integer type, and then you can do operations like set, clear, and insert. You can only do modification stuff on this. You cannot read back information from that particular register. If you want to read the register, you can literally just read the register directly. This object does not need to have more APIs to allow you to do that. You can just read it directly if you wanted to. When this object goes out of scope, it saves its contents to this object here. So it stores everything inside of a temporary, and then on construction commits those changes. You can also do chaining, which I don't know if I have an example in here. Oh yeah, so you do modify, and then you do set, and that will do what it needs to do. And you also have clear here as well. And then because the object was created at this point and then immediately gets destroyed, it gets created, updates the temporary, then saves the contents, and then returns. The compiler usually sees that and can compile it, optimize it down quite a bit. So when it comes down to how optimal this is, it should be quite optimal. If you want to extract a certain portion out of the register, you can use the extract function. So hal bit extract, you give it your range. I'll talk about more of that in a sec. It's the same as we had for bit set, but I'll go over it one more time here. And then you pass in the object that you want, or the register that you want to have the bits extracted from. I didn't include the information about the bit masks. So here we now have hal bit mask from. So you say you're creating a bit mask, and you're saying I want the bit mask from the point 0. There aren't any multi-bits here, but usually you do from 0 to 5, and that will create a bit mask of position at 0 of width 6 bits. And that mask will be here, and then you can put that mask into, you can use that mask to set, clear, do whatever you need for those particular bits you're trying to manipulate and modify. One key note for everyone here, if you end up using the bit library, always favor the template version of it. There's also another version where you can put this information into the first parameter and then put your register, just put it into the first parameter. You want to use a template version of this almost always, and if you can't, because the particular mask is known only at runtime, yeah, but basically what I'm trying to say is that if you use a template version of this, it's likely that almost all this code will be crunched down into a very small, very optimal bit of code. Basically, it's just optimization. The compiler has more information about the mask, and I should put this, has more information about the mask, and by knowing all the information about the mask, it can better optimize the code at compile time. So yeah, there's none of these that actually use the runtime version, so that's pretty good. Yeah, so that's that. So that's the bit library. It really just only has like the modify function, and then another one called value, which just allows you to manipulate stuff inside of a value directly. That's not from a register, and then extract. That's pretty much it. I'm considering adding another function called probe, which just pulls out a specific bit. And that'll be pretty much it. But yeah, that's pretty much how bit. Any questions, comments, concerns? Cool. Next up, we have libesp8266. The waited for library is a collection of libhal capable drivers for the ESP8266. This is currently a device drivers library. It is not a target library. So potentially in the future, we may actually target Tensilica-based CPUs. If that didn't make any sense to you, basically the ESP line of microcontrollers uses the Tensilica architecture for their boards. Now, I think they've jumped ship from that and have now moved over to RISC-V, which is great. For those who may not understand all these different terminologies, you've probably heard of the Intel processor. You probably have one in your computer. AMD and also ARM. These are a category of, or a instruction set architecture, meaning that they certain types of bits and pieces, the instructions that the machine reads to make you do computation. There are more architectures than just Intel, AMD, and ARM. There's MIPS, there's Tensilica, there is RISC-V, and a whole bunch of other ones. I believe MIPS was actually what the PS1 was using. Yeah, the PS1 CPU, I believe, was a MIPS processor. Could be wrong there. All to say that the ESP has the Expressive, the company that makes them, has been a little bit weird when it comes to data sheets in user manuals when it comes to their chips. I think mostly because they want to have ownership and full control over the software development kits for them. I didn't really like that too much, so I kind of decided I didn't want to really try to support them directly. But maybe in the future we will. So keep that in mind. But for the most part, a lot of these libraries are just going to be how to use them as external devices and less about how to program on them. So first off, I'm just going to give you a little tour of libesp8266. It's like any other library. I still need to update the README here. We have some AT command libraries. So everything's done through AT commands. Little helper note, if you, on the Expressive website, they say, oh, use the 2-point-something versions of the ESP8266 library, because those are the ones that we're actually working on and updating and continue to support. Those I could not get to work at all. I had to use their older, non-supported APIs to get things to work. I don't know why that stuff's broken, but it is, at least for me when I was testing things out. I just pretty much ended up breaking my devices and I had to re-flash them with something else. But we have a WLAN, a wireless LAN client object that just allows you to connect up to some SSID and some password. Some access point using an SSD and a password, and some serial port, and how much time you want to wait until that thing times out, or does or does not actually fulfill your request. And yeah, then you can use this in order to generate sockets, TCP sockets, which can then be used to, or actually I said TCP. I meant to say any type. It could be TCP, UDP, or technically SSL, or the SSL one I haven't been able to get to work. And you can then use the socket to talk to servers. So I'll go into more detail about that a little later. Actually, I'll go into more detail about how this is done, how this is designed, as we go a little bit further. I have some examples when we go into how we do parsing. But for now, that's pretty much what we have here. We also have a demo, which I'm going to show you here. That's a little step right here, the multi-target demo. So we have a demo for just a basic WLAN client that also can talk over the TCP. And we also have an example that uses the HTTP utility. I'm going to first start off with this portion. What? Oh, it's one of the older. Yeah, it's fine. Yeah, I'll show you what the multi. Oh, this is not. This particular commit is a bit too old, so I need to actually change. I need to change the links here, but that's not too big of an issue because main will have the updated version of this. So this particular application function takes in some hardware map, PMAP, and I'm going to go into more detail about this in a sec. But for now, we can just kind of go with the flow. It comes with a counter, some ESP serial, and some debug serial. We use debug serial as our print function, or as our serial to print out messages. So we have ESP Wi-Fi application is starting. We have some buffer that's 8K. We create a wireless LAN object. You pass in a SSID and a password, as well as also the timeout, as well as a timeout. We check to see if it's fine. If not, we return the error, as well as also saying that we failed. If that all worked out, we pull out the actual WLAN client object. We then use that in order to create our socket. You pass in the WLAN client. You pass in what type you want to be, which is TCP in this case. How much time you want to spend connecting to the server. In this case, we're connecting to the example.com server at port 80. To make sure that worked. You can also move the object out if you want to. And then finally, we make our GET request. This right here just fills up the buffer, the 8K buffer with dots so that you can see where things were filled and not filled. You send out the request. This is doing debug messages here. You send off this GET request you write it to the server. Wait about a second, and then try to see if you can retrieve the data back, get the data back, and then you can print it out. This is just a little helper function to print out the data. Oh, it also prints out the parse data. Wait, what? Oh, I guess it's another utility that added in. Yeah. So this is a very basic bit of code in order to send and receive data back from a server. It doesn't need to be HTTP. It can be whatever the heck you want. But in this case, we're just using example.com, which has an HTTP server, so we can talk over HTTP to it. Now, before we go any further, I really want to go into this little bit here, the multi-platform portion. If we go over to demos, this is pretty much what you would need to build a libhal demo. You'll have your toolchain CMake file for ARM Cortex stuff, or for the ARM compiler. New lib libraries just to get the compiler to shut up about not having these things fulfilled. These are things like writing to standard out, reading from standard out, closing files like that, which we don't have or support for this particular demo. So we just do the basics such as returning 0, returning -1, and stuff like that. Our main application is basically just including our hardware map. We run initialize target, which I'll show you in a sec, to make sure that succeeded. If not, we will halt and spin in a loop forever. If that was successful, we grab out the value. We then pass the hardware map into the application, which is what I showed before. If that ever returns back, we check to see if it's finished. And if it's not finished, meaning that it returned an error, we reset. Otherwise, we halt here. And then this little part here is just to make sure that boost leaf knows whenever there's an exception that was thrown for whatever reason to just abort the program. This is your reset handler, basically, effectively. Now, the cool bit here is that there's this new folder called targets, and each one of them has its own little target that you support. In here, we'll have an initialize your CPP file, and you have your initialize target, which does a couple things. Number one, it does all the initialization that it needs to do itself, such as initializing its data section, initializing the floating point unit, setting the clock speed to some value. I mean, in this case, we have 10 megahertz. Maybe we can have some configurations for different versions, but the one that I have on my SJ2 board is 10 megahertz, so you can switch this to whatever you like. Setting up your hardware counter, getting your UART ready, getting your other UART ready, and then returning. Oh, sorry about that. Returning back a hardware map. Now, the hardware map object incorporates all the pieces that we need for our project to work. Well, we need a serial for debug, just to print out stuff. We need a serial for the ESP itself. We need a steady clock object or counter. And then we also need some type of reset function. The reset function may change depending on if you're running on a ARM Cortex device or on a RISC-V device or whatever. Reset could also mean something very different depending on if you're running on a single board computer. We're not trying to really reset the entire computer unless that's what your project's plan is to do. Depends on what your application's needs are. So this is our hardware map, and this is how you would basically build out your project to be multi-platform. You specify the minimum necessary components that you need for your project to work, and you create a map of all those objects, and each target needs to basically fill out those objects for you. Now, you may be thinking to yourself, well, what about, like, let's say you have an accelerometer. Should that be in there? It's like, no, it should not be. You want this to be target specific. The idea here is that you need your I2C, your SPIs, and that kind of thing, and then you would use in your application, you connect those up to those devices, or to those device drivers. And if those fail, you know that you're missing some parts. So this is like the minimum stuff you get from your target device for everything to kind of function appropriately. And in each project should have an application function that takes a hardware map and does its duties to make the application work. And also should have an initialized target which returns back a hardware map. Does that make sense so far? Any questions about that so far? Just check to make sure I'm still online. Just make sure I haven't been talking into the void. Everyone there? Anyone there?
Yep.
Cool. All right.
Yeah, I hear you.
Awesome. All right. So that's the hardware map. Linker script that you may also need as well, the common linker script. Conan file will tell you what you need, such as in this case, I just have LPC and lib ESP8266. And yeah, then we have the applications. So from here, we have a couple helpers here that just kind of make our lives easier when it comes to printing out stuff and mirroring some serial stuff and that kind of thing. But yeah, we have the WLAN client here. We're just kind of pulling out these variables out into references so we don't have to do asterisks for every single one of them. And it's the same old thing that we saw before, just using the hardware map. In this case, we have the HTTP GET, which does almost exactly the same thing, except once you hit this point here, you run the HTTP GET create function to create a GET request. Pass in a socket, a buffer that you want it to go into, the path that you want to go to, your domain that you're trying to access, and your port number. And there's this thing called try until. I'll show that in a sec. That pretty much keeps running this thing until eventually either the timeout runs out or until the GET request is finished. And then we can actually print out all the information from the GET request. You can just run this multiple times over and over again to keep grabbing more data from the server. And yeah, that's pretty much the ESP library so far. You can dig into the actual libraries deeper to get, how things are going. It's not fully unit tested. There's still a lot of things that are missing in the unit tests, as well as also the libraries themselves, but it's a work in progress. Now, next up is going to be describing how this thing works, but some of the building blocks that are going to help us to be able to develop really good libraries that are hopefully easier to read. So first I'm going to go into worker objects. Worker objects are non-blocking coroutines or coroutine-like objects. Currently, we don't actually use C++ 20 coroutines, but I do plan on adding support for that in the future, just not at the moment. They perform some work until they run out of work to perform, or they reach some timeout, or they reach some condition that bails them out. Worker objects can be in either of these states, which is in progress, finished, or failed. Say and failed, but or failed. So an example of a worker object would be, let's say you are you have like access to some SPI object. You're talking. Oh, actually, here's a good example. Here's a worker object for the SD card. For SD card initialization, what you have to do is set the clock rate for your SPI to some lower value and then continuously clock the device. I forget when this phase happens, somewhere in the beginning. But you continuously clock the device until eventually it sends you back a sequence of bits to indicate that it has successfully synced up with your clock rate and has successfully initialized all the way, and then you start talking to it. So what you would do is you give it some SPI. You say, hey, look for this particular bit stream or something like that. And then you continuously call that object after you created it, and it'll keep streaming out bits and bytes. Or it'll keep running through stuff, and it'll keep reporting back in progress, in progress, in progress. And you can tell it maybe when you initialize it how many clock cycles you want or how many bytes you want to read in before it should bail out and say just in progress. So it keeps doing its work up until the point where it finds the sequence it's looking for. When it finds it, it'll return back finished. If it finds some condition that represents being failed, a failed situation, then it'll return back failed. And these objects might also have additional methods in them so that you can inspect or get information about the current or like the final finished product that it was working on. I'm going to show you some examples of that in a little bit. So that's just kind of the worker object. It's something. It's a callable object you can continue to call that will either tell you if it's in progress or if it's finished. And the whole point is that it's meant to be non-blocking as much as possible so that it doesn't use up too much time. The other object, the other setup here is this thing called byte stream pipelines. Byte stream objects are coroutine or coroutine-like objects that take a span of bytes through the pipe operator. I'll show you what the pipe operator looks like in a sec. Pipeline objects are in search of a particular sequence of data and will consume data from a span until the sequence or condition has been met. If a pipeline has finished parsing, it will return the remaining data from the span. So an example of a pipeline would be this. You have some input data that you got from somewhere, SPI, serial, I2C, whatever. And then you pipe that information into this sequence of pipelines. The first pipeline object is going to try to find a header. Next one is going to skip a byte for whatever reason. Let's say this is how how this thing's set up. It'll then parse some command integer, then read data into a buffer until it finds an end token. And then if it ends up doing all this work and has some data left over, it'll spit this out through remaining. Now, that's a lot of stuff to kind of just take in. We're actually going to show you some examples by looking at them in use with the ESP library. These were built to make the building the ESP library easier and better to understand. So first off, let's look at some worker object stuff. Oh man, wait, what? Oh, okay, hold up. That link is messed up. All right, well, we'll just take this link here. Oops, daisy. Kill that. libhal /libhal. libhal. I think that'll work. Nope. Main. All right, time to just go to it directly. All right, include serial coroutines. Not really coroutines. But here we have a couple of these items here, like skip past. And read into and read up to. What you do is you pass them a serial object, you give them a sequence you're looking for. You also give them a read limit, how many times you want them to read before it should bail out. And what it does is every time you call its parentheses operator, its call operator, what it'll do is it will it'll keep reading out of serial until it finds that sequence. And if it can't find it after we've reached a certain limit, then it'll return back in progress. If it ends up finding it, it'll return back finished. And it'll ensure that each time you call it subsequently, it'll always return back finished. These objects are nice because you can do something like this. So if we go over to... it's a good one. Yeah, let's go to WLAN client. So here when we create a client with the ESP8266 with AT commands, first thing we do is we configure the serial, we flush any data we may have, we create the object, then we run reset and connect. So reset, over here, first thing we do is we send out a string like this, AT plus reset, carriage return, new line. Now we have to wait for us to get back an OK message. The OK message takes this thing called skip and reset complete. So let's look at reset complete real quick. Reset complete. Oh, that's in utilities. So basically the reset complete or OK response, basically reset complete happens when you see the message ready, come back to you. So at util here, reset complete is ready/r/n. Now the thing is, the device, when it's resetting, spits out a whole bunch of log information. It's not just ready, new line, carriage return, new line. It spits out a whole bunch of different data, and what you need to do is you need to parse through all of that data until eventually you find the reset complete sequence. When you find that, you know it's finished. So what we do here is you can either call this in continuously, or you can throw it into a try until function, which basically continuously tries your function until it returns back failed or finished. You can also pass it a timeout to say how long you want to wait until that thing's finished. And that's pretty much the skip worker. It's a function that you can create. Actually, you can see here, you have a skip function. It's called skip passed. You pass it in a serial, and you pass in the string that you want to find, and that creates back the object. We basically just take this object that it passes back, pass it into try until, and run that up until it's finished. We also have another function called wait for OK. Basically, a lot of these commands will return back the message OK with new line /r/n to say that they're finished doing the work that you asked them to do. And we have to wait for that. So we can wait for OK, skip until you find the OK sequence, and delay up to this point. And yeah, so reset pretty much does that section here. Wait until you see the resets done, and then wait until you see the OK after sending in this thing to return off echo responses. And then when it comes to connect, you pass in your SSID and your password, and you also pass in your timeout. And it'll go through the sequence of writing data over to serial to tell the thing to connect, and then you're waiting for the OK. And that is pretty much that part, the worker side. So that's the worker side. We'll go into the pipelines in a sec, but just before we move on, anyone confused by this? Anyone have any questions about how workers work? Okay. Next up, we have the byte stream pipelines. I don't know if this is a full link. Yes. So here's some of the streams that we have. They're actually almost identical to the coroutine, the work objects, except they work a little differently. So we have find, and this thing works through the pipe operator. I'll show you what that looks like in a sec, but it looks pretty neat. If you've ever done a lot of work with Linux, you'll find that this will probably feel a little bit similar to piping the output of one function into another one command into another command into another command. So you pipe in some span of bytes. It then does some work on that span of bytes, basically looking for that sequence. In this case, this is called find. You try to find a particular sequence. When it finds that sequence, what it does is it returns back a subspan of whatever was left. So as an example, let's get rid of this. If you have A, B, C, D, E, F, G, that's in your span, and you pipe that into something that's looking for C, D, E, what will happen is it'll look at A, throw it away, look at B, throw it away, look at C, okay, that works our sequence, then D, then E, oh, we found our sequence. So then what it'll do is it'll send out FG as the remaining span information, and it'll pass that on to the next item in the pipeline. And the next one go, oh, well, I'm looking for an F. So we'll split that up, take that out. Let's say the remaining is now G, and then G might just be the remaining little bit of data that isn't useful anymore, and then that can go somewhere else. So that's kind of the main idea of the spans, or like for the streams. There's a find, there's a fill. Basically, you can fill a buffer up until it fits a certain amount. So you keep piping in data into it until it fills up something. Fill up to basically fills until you find a sequence. And then also parse, which actually parses integers for you. It doesn't do floats yet. We're working on that. And then skip. Skip a certain number of bytes inside of the span. And yeah, you can use this to compose really, in my opinion, expressive pipelines to break up discontinuous data into sections. So let me show you. Let's look at libhal ESP, and let's look at the HTTP utility. Yeah, nice. We're going to skip ahead, and we're going to go over to its worker state. So this is also another work object. And here you can see we We read out some bytes from the socket. This is not a serial read, this is a socket read. We grab out the data. Then what we do is we pass this up to our pipeline. The first item here in the pipeline is find content length. Next one is parse packet length. After that is then find the end of the header. So what happens here is, let's say we only got like 3 bytes. Well, you'll pass those 3 bytes into find content length. Those 3 bytes may not have the content length information. So what happens is if it can't find anything that looks like content length, what it'll do is it'll consume those 3 bytes, return back empty to this, which we'll see, oh, there's no data here. It'll return empty as well, return to this, that also is empty, and then continue on. You basically pipe information in from the start here to the end, but each one of these doesn't really push what it found over. It basically fills up or consumes as much as it needs until it's hit a certain condition and returns the remaining to the next section here. This one becomes labeled as finished and then pass the information to this guy. And what happens is if you run this loop again, this one will say, oh, I already found the header, so I'm going to pass everything I saw to the next item. And this one then keeps doing its thing until eventually it finds it skips its bytes it needs to skip. Then you pass information to this guy, and then this one, and then so on and so forth, until eventually you have finished all of these.
Does it define its header based on beginning and end, or is it just a space definition, or can it be just up to the user?
Oh, that's 100% up to the user. Like these are ones that we've created ourselves. This thing just finds a sequence. The sequence is up to you, what you want to sequence for, which you want to look for. For example, mFind content length is defined here in where did I put it? Where are you? Right, it's constructed each time at the start. So yeah, find content length basically just looks for this message here. Content length, colon, and a space. The next one is parse packet length, which is literally the text afterwards. To show you what I'm talking about, I can actually look at HTTP response for this. Ooh, wow, that's a lot of tables. For this thing here. So let's go to network here. Let's refresh again. That's a hard refresh. I should be able to go here. I should be able to copy this. I want to copy the response. Let's see what we got here. That might be too much, or not the right stuff. Ooh, baby. All right. All right. This is the response, but not the header. The header, I always forget where to find it. Header options. There's a way to do this. Is it in here maybe? Response. No. Headers. Give me 1 sec as I find the header I'm looking for. Maybe if I do copy here. Is this gonna give me everything I need? No. There was something here before. I'm not gonna take up too much here this time. Basically, I'm just gonna copy, I think sfetch or scurl. I think that might give me what I'm looking for, at least temporarily. Oh no, that's not what I want. That's not what I want at all. Basically, it looks like this here, and if I can get this guy copied over. That's not the full. I don't think that's a full response header, or that's a response header that's not for. Yeah, we'll ignore it. We won't be bothered by it too much. Oh, actually, this one looks good. This is the one I'm looking for. This looks better than what we saw before. But basically, HTTP request headers usually look something like this. Actually, might be able to. Yeah, I'll stop there. But basically, they usually look something like this. There's more fields that are supposed to be in here, but you'll see a content link that looks like this. It doesn't look like that exactly. There's a way that it's supposed to. Actually, I know what to do. HTTP request. Mozilla requests. Oh. Real quick. Okay, just making sure I'm still online. Let's look for response, actually. I bring this up because you're going to see that this thing has quite a bit of fields on it. that response. This is not looking for either. Wow, I've literally been using that particular thing for the longest time, and I cannot seem to find. Oh, here we are. All right, it normally looks like this. 200, okay. A couple other information here. We have this one does not say content length in here, but it usually does. And what you want to do is after you get this data here, you also get it tells you how much. So the HTTP response looks like this. It tells you what your status is. After that, in somewhere in here, you'll have content length. And then after you hit the end of this part here, the header, you have a new line, basically an empty line. And you have all your content afterwards, and you can read that information in. So what we have to do is we need to parse out the content length. And once we find that content length has been parsed out, we can then, where is it? Start actually just reading data from the serial port to gather all the rest of the data into some buffer. So this pipeline pretty much does the work of finding the content length, parsing the length information from there, and then finding its way to the end. And when we find our way to the end, we can then check to see if that particular find to the end has been terminated, basically meaning that like this thing succeeded at some point after some number of calls to this operator. And when that happens, at that point, you know that you're pretty much in a state where you should be basically reading all the rest of the data into that buffer. So this is one small example of showing this off. Another example would be with the AT commands for socket, I believe. Where is the read operation? Yeah. So here, we have this thing called find header. Yeah, so find header, what it does is you basically read one byte at a time. You pass that byte over into this particular stream of find the start of the header, parse the packet length, and then skip a colon. The way the packets are set up for the ESP8266 is it goes looks like this, plus IPD, comma, some number that tells you number of bytes that are going to be in your packets, let's say 2050, and then a colon, and then you have a whole bunch of other data afterwards. Now, this may seem pretty reasonably easy to parse out, but there's still, like, I would say having to build the state machine to kind of handle all this and then to parse all the information and dump it all into a buffer is a lot easier when you can just kind of pass it through here. And this also allows you to do, this may seem like a lot of effort for something that's only a very small format, but when you have very large formats, like very bigger serial stream formats, pipelining it can be a really good way to make that a lot simpler for yourself. Versus having to make the state machines yourself. So that's the idea of pipelines. And at the end of this is that usually you sometimes do, like, let's say, I can copy this real quick. Hold on. Auto remaining is equal to this. It's likely that you may want to know how much data that you read in. Let's say you read like an entire 1 kilobyte and you actually finish this up within like the first couple bytes. You want to use the remaining for other things, such as maybe you're going to pass that into a buffer, copy it into a buffer, or you're going to toss it or do whatever you need with it. But the return type of after all of this is basically just another span. So that's how byte streams work. So that's kind of how you'd use them. And that's pretty much it for these meeting slides. So for everyone who's been watching online, I'll see you next week.